Welcome back to lecture 11, sorry, I keep saying 11, 14.2, where we're going to define a Carnot refrigerator. Okay. So remember last time we were talking about the Carnot efficiency of an ideal gas. We drew our standard heat engine diagram. So this was our engine. And we talked about inputting some work, right? From some other kind of engine, running my Carnot cycle backwards. And we asked, what did we get? If instead of we have the heat flow out of the hot reservoir, right? Let's just take our entire cycle. Remember, everything in our Carnot cycle is reversible. We have isotherms and adiabats, so everything is reversible. So let's just reverse it. Instead of getting work out, let's put work in. Our heat then flows from our cold reservoir to our engine, and from our engine to our hot reservoir. So, is this consistent with the the second law of thermodynamics? Well, heat is flowing from a cold reservoir to a hot reservoir, but it's not spontaneously doing it, right? We had to actually do work, and so this is why it works, okay? So, is this an engine? Or is this another object? Right? So it's actually a refrigerator. Wait, how is it a refrigerator? Well, a refrigerator takes a cold body, right, the inside of your home refrigerator, for example, and it extracts some heat from it. And to do that, you actually have to put some work in. Your home refrigerator is through a compressor. And then it's going to dump the excess heat out to a hot reservoir. In your home refrigerator, that's the room, right? So you're taking the cold air out, doing some work, and dumping the hot air to a hot reservoir. Pretty awesome, right? So the refrigerators in my lab get much colder than the one in your home, but they still obey this idea of how a refrigerator works. Okay, so when we think of a refrigerator, now what is the efficiency of a refrigerator? Well, what do we want? We want to extract as much heat as possible. And what are we putting in? We're putting in work. Okay, so this is how we define the efficiency. So let's put a little R here for refrigerator. So this is the eta of a refrigerator. It's supposed to be like a superscript R. But still, so we have, this is QH minus QC is the total work. And we showed last time, this could be rewritten as TC or TH minus TC. Okay, so let's inspect the conditions that we get for the performance of a refrigerator, right? So when is it high performing? Well, what happens, for example, if, well, let's see. Let's imagine the following situation. Let's say you have something cold in your refrigerator and it's cold in your room. Okay, your hot reservoir is cold. If this delta, let's say it like this. If TH minus TC is small, right? So that would be a small number. It's larger than eta of a refrigerator is greater than 1. Okay? So how do you have a something that's greater than 1? Well, we don't call it an efficiency, we call it a coefficient of performance. So eta is our coefficient of performance. So the higher the eta, the more performing it is, right? That is, the larger eta is, the more heat we're extracting for the amount of work we're doing. So we want eta to be large, and so we want eta is large. So eta large if TH minus TC is small. And eta is large if TC is large, right? Okay, so this is two really important things. One is a refrigerator is most efficient if you have very little temperature difference to make up, right? That's opposite of the engine that we saw last time. An engine is much more efficient if the temperature difference is very large. So here you want the temperature difference to be small, but you also want TC to be large. So your home refrigerator can be quite efficient because the temperature difference between, say, the room and your refrigerator is very small. Let's say your refrigerator is at 4C, it's 22 or something out in your room. Then your efficiency can be quite high. And TC is relatively large, right? So that it's 277 Kelvin instead of much colder, right? Okay, now this is really important because as TC goes towards 0, then eta R goes to 0 as well. So for a low temperature physicist who's always trying to get things colder and colder, this is quite a statement, right? That as we try to get colder and colder and colder and colder, our efficiency of our refrigerators goes down and down and down and down. So we have to do more and more work. So the job of a low temperature physicist just keeps getting harder and harder and harder as you go. Okay, next time in lecture 14.3, we're going to talk about one more possible configuration of the Carnot engine.